Okay, so I think we can start. Is it, yeah, is everything working? Yeah, seems like it. If anything is not working, please let me know. Okay, so now that we've understood isolated singularities, let's talk about something a little different. And what I'm gonna do now is just first give a formula for counting the number of zeros involving integrals. Right, this shouldn't come as a surprise because right, we've done already things of this style in a way, right, with the winding numbers, and then we're gonna try to understand how functions map sets into nice sets into nice sets. Okay, so let's say, okay, let's set up an object again. So let's say f is an analytic in an open disk, right? So, okay, when I say disk, I always mean open, unless I say otherwise when we write open disk. And again, f is not identically 0, right? That's not interesting. Identically 0. Okay. And let's say also, although this is really, as we'll see, is really not important, it just will help us do the calculation, and in the end, I'll argue that it's not needed. Let's say f has only finitely many zeros. Finitely many zeros in the open disk. Okay, this won't actually be needed, but right. Notice that because of the identity principle, it could for f to have infinitely many zeros, it couldn't have an accumulation point. Right, so it couldn't have been that you had infinitely many zeros with an accumulation point in the disk. What could happen, however, is that they have infinitely many zeros with an accumulation in the boundary of the disk, and so it's not at a place where it's analytic, and so right, the identity theorem no longer applies. So potentially you could have a function with infinitely many zeros as long as you have the disk here and the zeros accumulate towards the boundary, right? And if you don't know that the function is analytic at the boundary, there it's anyone's game. But okay, let's say that it has finitely many zeros, right? And let's call the zeros z1 all the way to zn, right? The zeros of f, right? Where counted with multiplicity. Right, so if a zero is a zero of order 2, then I'll answer this question in a second. There was a question on the chat. So if a zero is a zero of order 2, then it shows up twice in this list. Okay, maybe I should write that specifically, right? So if z, or say a, is a zero of order k, it shows up k times in the list. Okay, so good question. So aren't these two statements equivalent, right? Because of the identity theorem. So the reason why they're not equivalent, they're almost equivalent. The reason why they're not equivalent is that you could have a function that, right, is sort of this example that I was trying to convey. So, but it's of course a very good question. Let's say I have a disk, right? And now I draw the zeros. If I have, what I know is if there's an accumulation point, right? If there's a point such that I have infinitely many, right? Or I have an accumulation point of the zeros to there, then the identity principle would tell me that, would tell me that this could not, that this function would have to be identically 0. However, what I could have is infinitely many zeros where they accumulate towards the boundary, right? If I have a set, then if I take it with the boundary, this is compact. So any set, if it's infinite, it will have to have an accumulation point, right? But the accumulation point could be at the boundary, and f doesn't need to be analytic there. Right? Okay, someone give an example even. All right. Okay, so, but it does imply that for any slightly smaller disk that I consider, there can only be finitely many in that smaller disk, and that's basically how we're going to get rid of this assumption. Okay. All right, so now, let's say that, okay, so now let's let gamma be a closed curve in the disk, right? Inside the disk. Of course, I want that, for all k, zk is not in the curve. Okay, so this is my construction so far. Oh, I was going to write in yellow only the thing that I wasn't going to need, and then I just forgot to switch to white, but okay, switch now. So, okay, so now it's clear because z1 through zn are zeros of f, right, with their multiplicities. I argue that you can write f of z, right, as z minus z1 times z minus z2, so on and so forth, z minus zn times g of z, right, where g of z has no zeros. Okay. Okay, why? I'll give you can prove this by induction, right? So take one of the zeros of f, let's say is of order k, right? And now write, right? Let's take the first, the proof sketch. Take z such that fz is 0 and say of order k, and now write f of z as equal to z, bad choice of letters. So take z1 such that fz1 is 0 of order k, and now take z minus z1, right, to the k times g of z, right? And now this has no 0 in z1, right? So now this function g of z1 is not 0, okay? And you haven't introduced any other zeros, right? Because z minus z1 is not 0 anywhere else, right? And so this function now has only n minus k zeros, right? Only n minus k zeros, right? And because if this is of order k, needs to show up k times in the list, right? This is exactly the same thing as just z minus z1 times z minus z2, right? Because they're all the same, right? Where I'm thinking of them as they showing up in the list and together, say, right? And now we have g of z with only n minus k zeros, and they're exactly the other n minus k zeros of f. So you just keep doing this over and over again, right? So you just use induction, for example, or you don't even really need induction, but okay, right? Okay, so I can write g in this way, in the way that f of z, g of z has no zeros in the disk. Good, so I'm going to erase this proof sketch. Okay, so now that I take this, I can take what we call the logarithmic derivative, right? Or the logarithm derivative. Right, this is a trick that we've seen before, logarithm derivative. Okay, the idea being to take, right, f prime of z, right? So, right, you can think of it as a logarithmic of the derivative, but you don't actually need it, right? You do not need to ever take a logarithm, right? You can just define it as f the prime of z over f of z, right? And so what is this? I'm not sure if the best way is to write it or just, maybe let me write it. Okay, so what shows up here, right? On the bottom, you have z minus z1 all the way, or z minus z2 all the way g of z, right? And what you have on the top, well, you have to take the derivative of this. But what's the derivative of this? Is, and you take the derivative here, which is just 1, and then you get this. So it's exactly this quantity again, right? So, yeah, okay, let me just write it down, right? So I differentiate this term, leave the other two. So z minus z2 all the way gz, right? Now plus, now I differentiate only the second one. So I get z minus z1. Now the z minus z2 goes away, z minus z3 all the way, right, gz, right? And I have terms all of this type, many, many of them, plus the last more interesting term is when I differentiate g of z. So I get z minus z1 on z minus zn, and then g prime of z. Right? So maybe another way to write this is if I call this some number sharp, then what I have here on the numerator is just, right? I have sharp divided by where I remove z minus z1, then I have sharp where I remove z minus z2, and then I have sharp where I remove right, z minus z3 and so on, and I have another one where I replace g by g prime, okay? So what this means, let me write now the formula here, okay? All right, so this means that f prime z minus f of z, right? Let's now write each term of the summand, right? So what is this term of the summand? This is exactly what's here, but there's a z minus z1 too many on the bottom, right? And then what is this term? Exactly the same thing, but with a z minus z2 plus so on, plus g prime of z over g of z, right? But because g of z has no zeros in the disk, this must be analytic, right? Right, because I constructed this with no zeros and of course an analytic. Okay, so what this tells me, right, I have this formula. Let me erase here. So now, right, so I have this formula. Now, of course, by Cauchy's theorem, on the disk, right, I immediately have that the integral over gamma, right, of g prime z over g of z dz is equal to 0, right? Because there's a closed curve, an analytic function, and it's a closed curve in a disk. Oh, so there was a question, let me clarify, of why we know that such a g of z works. So I sort of gave a sketch of the proof. Was this question asked before I presented a sketch or after I presented a sketch? Could you just clarify? So I can make the sketch as a proof a bit more precise. After, okay. So let's say that all the zeros are of order 1, right? Then if all the zeros are of order 1, then it's clear. Okay, let me make this a bit more precise. Right, so I have all these zeros. Now they are not, right, the zeros might not be of order 1, but if they're not of order 1, I repeat them whatever order they have. Right, so this is counted with multiplicities. What I mean is if there's a 0 of order k, it shows up k times, right? So now you grab the function f, and you're sort of going to be removing zeros of it at a time, right? And so if let's say that everything, all zeros are of order 1, just to start this way, right? Then f of z is equal to, let's take the first one out, z minus z1, right? Because it's a 0 of order 1, we know that this must exist, and g of z is no longer 0 at z1. Right? Also, g of z has exactly as many zeros as f had, except the one at z1. You're not introducing any more zeros, right? There's no way that right? Because I can take, right, outside of z1, I can just think of this as fz divided by z minus z1. Right? Or maybe another way is, right, if this function had more zeros than f of z had, then f of z would also have to be 0 there, right? And so g of z now has only, okay, right? So let me maybe, so g of z1 is not 0, and g now has n minus 1 zeros. Okay, let me call g1. Okay, so I took away 1 0. Now I just do it again, right? I take g1, right? The zeros of g1z are exactly the rest of the list, right? Because except for z1, the zeros of these two functions need to be exactly the same. And now I take g1 of z, and this is equal to z minus z2, right? Because z2 is the 0 of g1z times g2 of z, right? And again, same story. Right, and so, okay, let's see. Okay, that this is all clear, and if the zeros are of bigger order, then I take this to a higher power, right? And if I take this to the higher power, it's the same thing as just taking z minus z1, z minus z2, and so on in the entire list, right? And the reason why you can do this is what we proved about the zeros, right? What was important here was going back to this fact that we proved that if a function was 0, then not all derivatives could be 0, right? And the fact that not all derivatives were 0 allowed us to do sort of a Taylor-like expansion, where at the point at which the derivative stopped being 0, that function wasn't 0 at the point. And so basically what we showed via this identity theorem was that if a function has a 0 of order h, say, then I can write as z minus the 0 to the power h times the function g that's not 0 there, right? This was done via the identity theorem and this Taylor expansion. Okay, I didn't realize that was the part that was unclear. Right, we showed that if something has a 0, you can sort of divide it by z minus 0, just like in polynomials. Right, this was done maybe, I think, last Tuesday. Right, and then we even did that for 1 over the function to do the same thing over for poles and all this stuff. Okay, so we have this so far. So what does this mean? This means that the integral around gamma of f prime z over f of z dz, right, is equal to the sum, say, from k from 1 to n, right? Maybe I shouldn't choose k because I was using k for the order, so let me use j. J from 1 to n of the integral of f, oh, sorry, not f, 1 over z minus zj dz, right? Because this is never 0 in the curve gamma, and gamma never goes by zj's, right? This was what we the hypothesis we had here, right? But we know exactly what these objects are, right? These are the winding numbers. And so in particular, we get this very nice theorem that the integral around a curve, a closed curve gamma, of f of z prime over f of z, right? Let's do 1 over 2 pi I, just so that the winding numbers show up, are equal to the sum from j from 1 to n of the winding numbers of the curve and the zeros. Okay, so we get a formula that adds up the winding numbers. Now, of course, this is most useful when we know, right? It's very useful is when we know, so useful or most useful, when we know that, you know, n gamma zj is either 0 or 1. So for example, if I take gamma, oh, sorry. If I take gamma to be a circle, or if so, then okay. So all right. So this is most useful is when we know that this is 0, 1. So if the curve is a circle, then right. Then basically this is counting the number of zero. This is 1, right? And say, okay, let's call it C a circle, and CZJ is equal to 1 if this is inside the circle. Okay, we called I now don't remember if, because in the homework this was given a name. I now don't remember if it was a little ball in the bottom or in the top. I think it was in the top. So interior of, or I shouldn't call it interior, inside of C, right? And 0 otherwise. And so effectively what this is doing is counting the number of zeros inside a circle, right? So if, right, so take a circle or any other curve that, that every point is winding number only 0 and 1, then 1/2, right? It does not need to be a circle at all. Of course, it can be something like this, right? It's just when you have stuff like this that you start having winding numbers that are bigger. But let's say a circle to keep things simpler, right? And this f prime z over f of z dz, right? Forgot a dz here. This is equal to the number of zeros of f in a circle, inside the circle. Okay, so this is a power counted with multiplicities, right? Of course. Okay, so this is a powerful formula, right? So we take an integral around the circle and we can count how many zeros are there inside. I mean, this shouldn't come as that big of a surprise, right? Because basically, the Cauchy integral formula is essentially this for the function z minus the 0, right? The simplest function with that 0. But still, it's nice that, you're getting out of an integral, you're getting information about the zeros of the function. Okay, so now it's useful. Let me address now the finitely many zeros. Okay, so this is actually not needed, right? Why do I not need this expression here, right? Because even if f has infinitely many zeros, right, it's very easy to just do the following. Just fix gamma inside your right, fix gamma closed curve inside the disk, right? It's clear that there exists another disk inside your disk such that, right, a slightly smaller disk, such that gamma is still inside the smaller disk, right? Because gamma is closed and the disk is open, I can just shrink the disk a little. And then from the identity principle, right, from identity principle, right, f has finitely many zeros. Finitely many zeros in the disk, and so I just apply the theorem to that smaller disk, right, and everything goes through. And so for any curve, right, this sum is always finite, right? And so I can have this formula with just infinite, just any amount of j without indexing, just for all j's, for all, say, zj zeros of f, right? Because the only non-zero terms in the sum there's only a finitely many non-zero terms in the sum always. Okay. All right. So now Okay, let's now see a few interesting implications of this. Okay, so it's clear that now you can do a fair amount of analysis potentially with this, right? Counting zeros and maybe estimating the amount of zeros, right? You can now estimate, could imagine that you can estimate number of solutions to equations by integrating around the set of solutions you're interested in, right? And things of this type. Well, let's take this into a somewhat different direction. Okay, and now you'll see this starting showing up, thinking of an analytic function as mapping complex numbers into the complex numbers, as we saw in the linear transformations or the bilinear transformations, in the Mobius transformations, in the Riemann sphere, and so on. So now what I'm going to do is going to be most useful to think of, right? So again, let's stay in the same object, right? F analytic in the disk. And now let's think of, right, the disk, or, you know, F, right? It's a function from the disk to C. And now I want to see it as a mapping that takes, you know, variable Z, right? What Alfred's in the book calls this the Z-plane and the W-plane. We haven't been using that terminology very much, right? But it goes to W, which I think of F of Z, right? And now I want to understand this mapping of what it does to a set, to a subset, or you know, any subset of the disk. It goes to something in the complex plane, okay? Right? Obtained by, of course, the function F. In particular, right? The curve gamma goes to some other curve, right, as you apply to F, because F is continuous, right? It will send the closed curve to some other closed curve. Right, this will be a closed curve too. Right, just imagine having the function F, right? There's the disk, right? F sends this to whatever. There's some curve gamma, and maybe, you know, F applied to gamma sends it to something, you know, that does to some curve big gamma. Okay. Okay, and we think this in, like, you know, to use the notation from the book, probably reading from the book, they call this the omega plane, or the W plane, right? But it's just, you know, in the image. So now, you know, just by a change of variables, right? If you take the integral of 1 over, right, say in these variables W, right, where W I think of F of Z, right, over this curve of 1 over W dW, what is this, right? If I don't do the change of variable W to FZ, this should be the curve over, right, the thing in the image. Maybe I should have put this on the left, right, of exactly F prime Z dZ over F of Z. Right, I mean, it's good to, you know, convince yourself of this if you have to doing the calculation, but this is like, right, the change of variables. Now, on the image, I have this integral. And so in particular, right, this integral is equal to what? Right? This integral is equal to the winding number of this image curve around 0. Right? While this we saw was the sum. Oh, I should put 1 over 2 pi I everywhere. 1 over 2 pi I. I don't know if I was missing a 1 over 2 pi over there, but yeah. All these integrals, of course, should have a 1 over 2 pi I. All right, this was the sum over j of the winding number around the curve of the zeros. Okay, so you know, let's think of the circle, right? Draw the circle around, right? Think of this, okay? Let's take gamma to be just a circle to be simpler, okay? Now look at an integral around gamma So now look at the number of zeros that it has between in the middle. What this is saying, I mean, and this is just sort of an observation, is that the number of zeros inside the curve is just given by how many times this image curve loops around 0, right? Let's say 0 is here, right? Let's say that this is a point 0. Then this curve loops around 0, I believe, 1 time, right? And so it would mean that there's 1 0 inside. Okay, I mean, just an observation from a change of variables. Okay, but now let's take this just a little step forward, which is instead of zeros, I can also ask for solutions or roots of FZ equals A, right? For some A. You know, nothing really changes if I ask for right? If I ask this for some A, right? They're just the zeros of FZ minus A, right? And so they can do exactly the same thing. And now I can call the solutions of this for some A. Let's call them solutions of FZ. There's that. Let's call them Z1 of A all the way to Zn of A. Right, and I mean, they may actually be infinite. It's the same setting as before, but let me call them this. Okay, so we call them Zj of A. Okay. So now, clearly, you know, I have the exact same thing, right? 1 over 2 pi I. Now, I just need to do the same thing for the function, right? I just need to do this exact same thing for the function fz minus A. The derivative doesn't change, so I get f prime of z, right? The bottom, of course, is different. Okay. dz, right? This is equal to the sum over j, over some curve, of the winding number around each of the points. So I can count solutions. Right? So I can count solutions around right around the point. Now, right, the same change, exactly the same, right? The same change of variable gives me that this is equal to 1 over 2 pi I. Let me give myself a bit more room here. Not have to cramp everything. Okay, so I get 1 over 2 pi I gamma of, you know, dw over w minus a, right? But I can think of this as n omega around a. Okay, same exact observation. But now what does this tell me? Right? This tells me that if I look at the curve gamma, right? So let, you know, making sort of simple someone asked if you get the number of solutions inside gamma. Yes, right? So if gamma is, again, something that for which the winding numbers is only 0 and 1, then this integral is counting exactly the number of times that the number of such solutions inside gamma, just like of zeros. Right? This is counting, right? So for a circle, say, for circle, this is equal to just the number of solutions or roots of the equation. Right? Okay. That's exactly right. Right, and I'm calling this, right, this object. Now, what does this tell me? And, you know, if you don't like the change of variables, there's a way of thinking about it without the change of variables, which is that, right, this has to be an integer. Okay, let me, you know, without making an actual proof, to me just be intuitive. This is an integer, right? So if I now vary a very little, right, you expect that this behaves nicely and somewhat continuously, right? And one can make such things precise. And because this is an integer, right, it can't change. Right? It can't possibly change when I just wiggle a. So what this is telling me already is the fact that because of this formula, and because this is tied to be an integer, that if I wiggle a little bit, then the number of solutions needs to be exactly the same. Right? And this is, if you think about it, it's quite special, right? So if I have a point, if I have a value that my function takes n times, then if I wiggle around a little, the function still has to take that value n times, right? Because this should move smoothly, and this needs to be an integer. But there's a nice way of viewing this in terms of winding numbers on the change of variables, right? But if you don't like the change of variables, you can think about it that way, right? Which is that if A and B, right, are in the same region of C without the big curve, right? Then we know that the winding number with A and with B are the same, right? And so this means in particular that the number of solutions or roots, of fz equals A is equal to the number of solutions or roots of fz equals B, right? Provided, that the curve only has winding number 0 or 1. Okay, and this is quite surprising, right? So it's telling, and in particular, for any value A, because the complement of the curve here is open, I can always wiggle it a little around a neighborhood of A. I always have that they are in the same region, right? So it's exactly that thing I said of the argument of wiggling a little. Okay, but so what does this tell me? Okay, so let's see in the last 9 minutes, which is I now get okay, let me use the same notation in the book so that then it's easier for you to read there. Right? Of course, I mean, maybe I should make this point a bit more precise, right? For any A, of course not in the curve, right? I mean, A being in the curve just means that f of z is equal to A in gamma, and that's bad news, of course. For any kind of, there exists a delta such that, right, for all B inside the ball centered at A and with radius delta, right? They are in the same part, right? They are in the same component in the same region, and so in particular, right, the winding number needs to be the same. Okay, just rephrasing what I just said. Okay, so there was a question. I'll address it after I finish. So, okay, so the theorem you get basically is if f, right, if f is analytic, right, it's analytic, say f is analytic, at Z0, okay. Right, then we have that, say, f of Z0 equals W0, right, some value. And let's say that f, right, I want to say that, this equation for any other value similar to W0 has as many solutions as this one has with W0, which is exactly the order of the zero. So fz0 W0 is a z, and, f z minus z and f as a zero. I should grammatically say this differently. And z0 is 0 of this of order n, sorry for the grammar, of order n, right? Then for any small enough epsilon bigger than 0, right? There exists a delta such that, right, if some other w minus w0 are smaller than delta, the equation, or let's say fz minus fz equal to omega has n solutions in as n solutions in do I need, yeah, in epsilon z, right, in z minus z0 smaller than epsilon. Okay, so now, okay, so if I have a 0 of order n, then for any value close to, or I mean, okay, if a function is equal to something, right, and now once I subtract that, it becomes a 0, right? If it's a 0 of order n, then if I just change this number a little bit, I get n solutions in the neighborhood for this, right, for the equation with a slightly changed value, right? And basically, we've proved this already, right? The proof, we've done this basically, right? The proof is sort of trivial at this point, right? So you take, right, you just need small enough epsilon so that f of z, right, you need f analytic, right? You need f analytic in the ball. Okay, so let's make even f analytic in the ball around z0 and say radius 2 epsilon. Okay, so there's epsilon small enough such that f is analytic there, right? Because we define f being analytic at a set as being analytic in an open set containing it, right? And now we can just take the curve to be the circle around, right? The circle around, right? And so is analytic, and pick it also such that this equation, right, such that fz minus w0 is not 0 for any other thing in here, right? And fz is different than w0 for all, z minus z0 smaller than 2 epsilon and bigger than 0, right? Because this is a 0 of exactly order n, arbitrarily close to it, it doesn't have any other 0 because of the identity principle. So I just pick epsilon small enough so that, it's analytic and doesn't have any other 0. And now I just do the circle around z0 with radius epsilon. Okay, and now you just take omega such that the ball around the value w0, exactly what we did there, around w0 and delta. So take delta bigger than 0, such that this ball is all contained in a region delimited by gamma, right? It's contained in the complex numbers except for gamma. Okay, so, right, I mean, this is a lot of notation, but really there's no idea to it after we've done that. Okay, so now, just because of this, the n, right, n around of gamma around w0 needs to be the same as n around w, around any w, and so right? The sum of the solutions to the equation, right? All right, let me see this. The sum around for J of n around this circle and the solutions to the problem where you go omega, right, inside the circle, right? So for J, such that Zj omega is a solution to Fz omega in, right, omega minus omega 0 smaller than epsilon. Oh, Z, sorry, Z. Okay. Right, and this needs to be the same because those numbers are the same, needs to be the same as if I just do it around Zg W0, right? And so in particular, it means that the number of solutions, right? I know that this was a 0 of order n, there's nothing else there because I made this small enough, this is n, right? And so you get exactly n solutions. Now, it could be that you get some with higher multiplicity, but, right, so you could potentially get with higher multiplicity, but actually, it's not so hard to make sure that you don't get any multiplicity by just taking, if you just take epsilon bigger than 0 small enough, so that, right, you just get epsilon bigger than 0 small enough so that, say, the f prime of z is not 0 in z, let's say, or 2 epsilon even. Okay? This is not really important, but if you want to make sure that, that I really mean n different solutions, you just want to make sure that it doesn't have any other 0 of, right, that cannot have any other point that after you subtract its value becomes a 0 of order more than 1. All you have to do is to make sure the derivative is not 0, right? But, either you have n equals 1, and then they can't be higher multiplicities, or if n is bigger than 1, then you know that the derivative cannot possibly be 0 arbitrarily close of the point, because otherwise, the zeros of the derivative would have an accumulation point. And so because of that, you would have, the derivative would be 0, and so the function would be identically 0. Okay? So this stuff, and now we're going to get an implication of it. I've run out of time, so I'll do this implication on Friday. Let me just say it, which is that because if you wiggle in the image, you still have the same number of solutions, it means that the image needs to be an open set, right? Because I'm allowed to wiggle in the image, so the image must be an open set. And so this is how you show that this function takes open sets into open sets. And and so we'll see this on Friday. So just a note. So this, this particular proof or argument, there's really not that much to it. It's just that there's a lot of notation, right? So it's the kind of thing that is most effective if you sit down and try to reconstruct it, or read from the book, or rewatch and try to reconstruct it, because it's not the kind of thing that's so easy to see someone else do, because there's such heavy notation and so on that's sort of easier for you to just try to do it yourself, because it's really not that complicated. It just sounds a lot more complicated than it is because you need to introduce all this really heavy notation. Okay, so if this stuff sounded complicated, it really isn't more complicated than things we've done. I would say even less, but try to do it yourself. Okay? This is around, I don't know, in the book we're probably around page 140, something like this. Okay, so I'll stick around and happy to answer questions.